Okay, so now I'm going to give an example of using some of the Maxwell's relations to take you through identifying an equation of state, a thermodynamic equation of state from one of the thermodynamic potentials. Okay, so internal pressure is how the internal energy changes as you change the volume. For an ideal gas, this is 0. But it turns out that if you were to plot the internal pressure as a function of temperature, it's a linear relationship. And you can get from that slope, actually, it's not a linear, there we go. Pretend these dots are linear. Okay, so you plot the data and you get, so internal pressure versus temperature, you're going to have T times your slope, dTV. And so that slope then can give you partial P partial T with constant V, which you can relate to another thermodynamic potential. Okay, so we're going to show how you get this, or I'm going to talk out loud how you get this. So we start with U. So U is a function of pressure, volume, and temperature. And so we know that du is equal to TdS minus P dV. There's my Q. There's my W. And so this is from first law. And so now the question becomes, well, how does U change when I change the pressure at constant temperature? Okay, so partial U, partial P at constant T. How does U change when I change the pressure at constant temperature? And it's become partial derivative and not a total derivative because I'm holding the temperature constant. Okay, so this is equal to T partial S partial P at constant T minus P partial V partial P at constant T. Does everyone follow how I made this step to this step? I'm not doing this for your health. You should be able to do these on your own after you've seen this video and worked through some of the homework problems. In fact, the homework problems are going to guide you in practicing this sort of approach. Okay, using one of the Maxwell's relations, here's how they're so badass, is we can say then that partial S partial P at constant T is equal to minus partial V partial T at constant P. Whoa! So if I do that, and then I substitute this into here, this gives me minus T partial V partial T at constant P minus P partial V partial P at constant T. Cool. But we want to know specifically how U changes. So we're going to go over here. We want to know how U changes with the volume. Okay. And notice how we're not quite there yet. And then this. So this is partial U partial P at constant T. Okay. So I've just substituted this into here. Okay. I'm going to erase and move this back up to the top. Okay. Okay, so now I want to, so I've just relocated this up here. So now I want to look at partial U, partial V. So that, I mean, that was the goal. That's what we're looking for. But I have du partial U, partial P instead of partial U, partial V. How do I remedy that? Neat math trick. Here we go. Well, partial U, partial V at constant T is equal to partial U, partial P at constant T multiplied by partial P partial V at constant T. Do you see why? I have some friends in the mathematics department that might punch me in the face seeing me do this, but you know what? It works. So I can extend this into du dp multiplied by dp dv, and my p's cancel. Cool. So what I can do then is I can multiply this whole thing, du dp by dp dv, and then that will give me du dv. Pause and rewatch that because that's important. So this becomes dp dv at constant t times du dp at constant t, which is equal now. So now I'm just multiplying this by the whole thing. Okay, so that's equal to and I'm going to kind of do it out so you can see it, minus t partial v partial t at constant p multiplied dp dv at constant T minus P dV dP at constant T. Multiply that by dP dV at constant T. You can see now I'm now going rogue off of the notes because you don't need them once you follow the mathematics. All right, so this then, notice dV dP, dP dV. That cancels, that's glorious. Now notice this, partial V, partial T, partial P, partial V. Same math trick. Those are going to cancel. I'm left with minus T, partial P, partial T at constant, uh-oh. How does that work? Partial P, partial T. Maybe it's not as simple as them canceling out. Well, I can tell you that the Euler relation is going to make this constant volume, which is kind of nice. So go make sure double check that. So then subtracting P times 1. So this, and so likewise, this becomes the P's cancel and you're left with partial U, partial V, which is the internal pressure. La, 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 la. Okay, so why does this matter? So this matters because this is called a thermodynamic equation of state. And before, the equation of state that we've worked with has been the ideal gas law. But there are so many more equations of state that relate the properties. So U is a function of pressure, volume, and temperature. And if you want to know how do pressure, volume, and temperature change on a different surface by changing the properties, you can now learn a lot about the internal pressure of your system, and you have an equation of state to do that. Very, very powerful things. And so then now we would say, okay, well, is my system an ideal gas? If so, this is going to go to 0. But if it's not an ideal gas, if it's a van der Waals gas, if it's a mixture, if it's a fluid that has some sort of thermal expansion coefficient associated with it, you can now look at how the pressure and temperature change and relate that to the internal pressure. Or there are other thermodynamic functions you can also relate it to. This is just one of the examples. Go team.